Imagine a universe where time stands still, where gravity is but a mere illusion, and where the stars in the night sky are not what they seem. Welcome to the fascinating realm of physics, a discipline that doesn't just challenge our perception of reality, but also vividly influences our daily lives. Physics is all around us, in the swaying of the trees, the flowing of a river, the buzzing of your mobile phone, even in the simple act of flipping a switch. It presents a world that transcends beyond the ordinary, taking us on a thrilling ride through the intricacies of the cosmos, while simultaneously guiding us through the mundanity of life. Here, we dive deep into the enigmatic abyss, exploring theories and concepts that boggle the mind, and yet also have practical applications in everyday situations. The laws of physics are not just astoundingly intricate, they're also incredibly applicable. Think about Newton's law of motion when you're playing football, or the principles of thermodynamics when you're cooking your breakfast. Physics bridges the gap between the known and unknown, unveiling secrets that not only help us comprehend the cosmos better, but also solve everyday problems more efficiently. Today, we journey through 20 of the most important formulas in physics. But we won't just delve into the abstract. We'll also explore how each formula can be applied in everyday situations to help us understand the world around us and make our lives a bit easier. Welcome to this grand adventure through the wondrous universe of physics and its practical. First, we start by delving into the heart of the most famous equation ever discovered, Einstein's E=mc². This equation, cunningly straightforward yet deeply meaningful, embodies the idea that energy equals mass times the square of the speed of light. This inherently conveys a deeply profound reality within the world of physics. It clarifies that energy and mass are not separate but can essentially be switched, similar to two sides of the same coin. The speed of light, an enormous and mind-boggling constant, has a critical role to play in this. Its importance becomes key as even a tiny amount of mass, when subjected to this equation, can potentially convert into a staggering amount of energy. This principle forms the foundation behind the never-ending energy emanating from the sun and underlies the immense power held within nuclear weapons. Behind the sun's energy and the power of nuclear weapons lies here. Moreover, let us consider a practical, everyday example showing the application of this equation. When you heat a pot of water for your coffee, you're transforming electrical energy from the grid into heat energy, which then transforms into kinetic energy in the boiling water. Although the mass change in this process is immeasurably, it symbolizes the principle of E=mc², where energy is converted to mass and vice versa. Thus, E=mc² is not just a concept contained within the walls of a physics lab or the vastness of space, but it also subtly manifests in our everyday mundane activities. Next, we journey into the enchanting realm of quantum mechanics led by the guiding light of Schrödinger's equation. This equation is an intriguing tool that describes the evolution of a quantum system's state over time. Much like a weather forecast, it calculates the probability of a particle's location at a given moment. To bring this concept closer to our everyday reality, let's consider the electrons in a mobile phone's microchip. Using Schrödinger's engineers can predict how these electrons behave, allowing them to design faster and more efficient electronic devices. This is just one way in which this intriguing equation shapes our day-to-day lives. Schrödinger's equation is a fundamental pillar in physics, an essential element shaping our understanding of quantum theory. Its impact on our comprehension of the atomic and subatomic realms is unprecedented. It has revolutionized the field of physics, redefining our understanding of the universe's smallest constituents and ultimately the fabric of reality itself. A bedrock of quantum theory, Schrödinger's equation continues to mold our understanding of the atomic and subatomic world. Our third stop is Newton's law of universal gravitation, F=gm2r². This equation is fundamental to our understanding of the universe. It's the cornerstone of physics, spelling out the invisible glues that everything together. By it, every speck of matter magnetically attracts every other, their attracting force hinging on their individual masses and the space separating them. To understand its effect in our daily lives, consider this example. When you jump, You aren't just pushing yourself away from the ground, but the Earth is also pulling you back due to the gravitational force. This force of attraction directly relates to the product of their masses. The greater they are, the stronger the pull. Yet it also inversely relates to the square of the distance between them. The farther apart, the weaker the attraction. It's an elegant, profoundly simple law that governs the movements of our world and beyond. It's this law that keeps our feet on the ground, makes an apple fall from a tree to the ground, and the planets in their orbits. It's more than just a scientific concept. It's something that subtly but significantly impacts our everyday lives. Next, we delve into Maxwell's equations, a set of 4 integral formulas that provide a comprehensive explanation of the interplay between electricity and magnetism. They are the bedrock of any discussion about electromagnetic fields, serving as a conduit between classical and quantum physics. Essentially, they empower us to understand the behavior of electric charges and currents, and the resulting electric and magnetic fields. Furthermore, these equations illuminate the intricacies of field interactions, revealing the complexities of their mutual influence. This understanding paves the way for deciphering the characteristics and properties of light, radio waves, and indeed, the entire electromagnetic spectrum. To bring this abstract concept to life, let's consider a real-life example. Every time you use a microwave to heat your food, you're observing Maxwell's equations at work. Microwaves generate electromagnetic waves, a combination of electric and magnetic fields oscillating together, which are perfectly described by Maxwell's equations. These waves are then absorbed by the water molecules in your food, causing them to vibrate and generate heat. These equations are quintessential for understanding light, radio waves, and the entirety of the electromagnetic spectrum. Our 5th formula is the Drake equation, a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. This mathematical framework acknowledges the vastness of the universe and the potential for life beyond our planet. It delves into cosmic factors, considering star formation's prolific nature in our universe. It contemplates the number of these stars with planetary systems around them and the fraction of those planets that could potentially harbor life. To give a practical example of how the Drake equation can be used in everyday situations, consider this. Suppose you host a party and want to calculate the probability of your guests bringing a +1. You would take into account the total number of guests, analogous to the total number of stars, the likelihood of them being in a relationship, analogous to the stars with planetary systems, and the chance of their partner being available that night, analogous to the planets that could potentially harbor life. This equation is unique as it amalgamates astronomy, biology, and philosophy in an attempt to quantify the unknown. Despite not being a definitive law of physics, it encourages us to think, hypothesize, and imagine. It's not a law of physics, but it's a fascinating tool for pondering the possibilities of life. And next, we have the 2nd law of thermodynamics, which states that the entropy of an isolated system never decreases. To put it in layman's terms, this law implies that things in the universe naturally transition from an organized state to one of chaos. Think of it like this. It explains the reason behind phenomena like melting ice cubes in a room that isn't cold enough. Let's consider a real-life example that most of us come across every day. Imagine you're making a cup of tea. You pour hot water into a teacup and then leave it alone for a while. Inevitably, the tea cools down to room temperature, right? This is because of the 2nd law of thermodynamics. The heat from the tea disperses into the room, increasing the overall entropy. Much like the inevitable passage of time, things don't go backward. They march toward a state of disorder. The law provides a scientific principle to the seemingly simple observations in nature and our daily lives. It's why ice cubes melt in a warm room and why time only moves in one direction. Our 7th formula is Planck's equation, E equals sine hv. This scientific equation makes a significant contribution to the field of physics. It's a unique bond that connects 2 main elements, the energy of a photon and its frequency. This equation opened a new chapter in physics where it became possible to study phenomena on the quantum scale. These unique phenomena are based on the principle that light and associated electromagnetic radiation consist of discrete energy units. These units are often referred to as quanta or photons. It tells us that light and other forms of electromagnetic radiation are made up of discrete packets of energy called quanta or photons. To illustrate how Planck's equation can be applied in everyday situations, let's consider the example of microwave ovens. Microwaves work by emitting electromagnetic radiation at a frequency that matches the resonance frequency of water molecules. Using Planck's equation, we can determine the exact energy of these emitted microwaves. This energy excites the water molecules in food, causing them to heat up and thus cook the food. Understanding the core principles of Planck's equation is essential for the functioning of everyday devices like a microwave oven. And next, we look at the Lorentz transformation, a pivotal component in special relativity. This transformative equation, essential in the world of physics, offers a mesmerizing illustration of the relationship between space and time as observed by two individuals in relative motion. To understand its significance in everyday life, consider this example. You are standing still, and a car passes by you at a moderate speed. It turns out, according to the Lorentz transformation, that the time inside the moving car is slightly slower compared to your stationary position. This phenomenon, known as time dilation, is a direct manifestation of the Lorentz transformation. It helps unravel the mysteries of how we perceive our universe. This fascinating equation is not just a set of numbers, but a beautiful melody that sings the song of the cosmos. It defines the relationship between observers moving apart or together in terms of their spatial and temporal coordinates. It's the mathematical expression of the idea that space and time are intertwined into a four-dimensional fabric known as space-time. Our ninth formula, the Heisenberg uncertainty principle, tells us that we cannot simultaneously know the exact position and momentum of a particle. This principle confronts us with the concept of quantum uncertainty. A particle's position and momentum can't both be precisely determined at the same time. This constraint isn't due to measurement errors, but is a fundamental aspect of quantum mechanics. The more accurately we determine one of these properties, the less accurately we can determine the other. This direct relationship further emphasizes the uncertainty. It's a fundamental concept that has profound implications for our understanding of reality. To give you a practical, everyday example, consider a speeding car on a highway. Say the police are trying to measure both its exact location and velocity at the same exact time. They can either take a photograph, capturing its precise location at a given moment, but they wouldn't know its speed at that moment. Or they could use a radar gun to measure its speed, but the exact location at the moment the speed was measured would be uncertain. This cannot be resolved no matter how sophisticated the measuring equipment is. This is a simple analogy that illustrates how the Heisenberg uncertainty principle comes into play in our everyday lives. Finally, we reach our journey's end at the wave equation. This isn't just a mathematical concept, it's a world filled with intrigue and complexity. This equation represents far more than the mere sum of its numbers and symbols. It's a graphical representation, a snapshot capturing the essence of a wave at any given moment in time. This equation is a gateway that allows us to step into the realm of physical phenomena with a fresh perspective and understanding. More than just a tool, it's a lens we can use to explore and comprehend phenomena such as sound waves that enable us to hear, light waves that facilitate vision, and water waves that mold our oceans. There's no question that it's fundamental to our understanding of these phenomena. To bring this closer to home, consider the music you listen to while commuting to work. The sound waves that make up your favorite song have been mathematically broken down and transmitted over radio waves using the principles of the wave equation. The sound you hear is a direct result of this complex mathematical formula in action, a testament to its everyday application. This equation is not just a theory confined to a dusty blackboard. It is woven into the fabric of our day-to-day lives. In summary, these formulas might appear abstract and complex, yet they are the keys to decoding the universe's enigmas. They shed light on the mesmerizing and unusual truths of our world, from the tiniest particles to the vast expanse of the cosmos. They are like flashlights guiding us through the labyrinth of cosmic mysteries. They aren't just mathematical constructs, they are the narrators of the grand tale of our existence. Consider how the principle of gravity, encapsulated in a simple formula, governs not just the motion of celestial bodies, but also the mundane act of an apple falling from a tree. Or how Einstein's theory of relativity, while used to predict the behavior of stars and galaxies, also underpins the technology behind GPS systems that guide us home every day. These formulas and equations aren't restricted to labs and classrooms. They are very much part of our daily lives. The more we examine and question, the more chapters we unravel in this epic cosmic narrative. Every question sparks a discovery, and every discovery triggers a cascade of new questions. The universe's wonders are recognizing and understanding these equations can help us appreciate the everyday miracles around us, from the changing of the seasons to the flight of an airplane. They reveal that the world we live in is not mundane, but a realm of wonder and marvel, governed by the exquisite laws of physics. So keep exploring, keep questioning, and keep marveling at the wonders of the universe.